Hello everyone. In this session, we learn about activation functions in neural networks. In our previous sessions, we discussed about how a neural networks learns from the data, process of learning from input layer to the output layer, how data is flowed from the input layer, output layer, basics of a neural network, how it works. In this session, we will learn one important component of this neural network, activation functions. So, what are the activation functions? Activation function in a neural network determines whether a neuron should be activated or not. Let us see with an example now. Suppose I have one case where a insurance person is implementing a neural network. We take his data. In the data, we have some features like age, education, income, and savings. By taking these input features, my neural network is training itself or learning from the data set of this with these four features: age, education, income, savings, and it is trying to predict whether a person will buy the insurance or not. Prediction is important here. Here, to predict these things, our neural networks first gives weightage to each feature, like which feature is contributing more for taking predicting this whether a person buy insurance or not. We calculated a weighted sum, like for each of these features, like x1 is age, x2 is education, income. We calculated one weighted sum. So based on this result of a weighted sum, we can't predict it properly because values may range from at different ranges. Accurately predicting whether he will buy a insurance is difficult if we directly take a weighted sum. So we enhance this neural network learning purpose. What we do, we include one more layer, hidden layer. This hidden layer calculates two other extra features like awareness and affordability. These are input features: age, education, income, and how much he has awareness of insurance. Like one that is processed in one neuron, affordability is processed in another neuron. These weights are sent to the hidden layer, and hidden layer send output to the output layer. Now this is the final output layer that predicts if a person will buy insurance or not. Now problem in this network is that if we, without using activation function, if we directly take weighted sum, which neuron should get back rid of? After with these weights for a particular instance, shall I activate awareness neuron or affordability neuron? Decision is difficult because both of them, if they give the same value, situations where if they deciding which neuron to activate is difficulty. So to avoid this problem, what we introduce one activation function. So output of this weighted sum is sent as a input this activation function. The output of this activation function is sent as a input to another neuron. Like this here, this activation function basically deciding whether a neuron should be activated or not. Without activation function also, if we can do it, but most of the time without activation functions, it follows a linear regression model. Means a neural network will become a neural regression model if you don't use a activation function. Let us see why it is a linear it becomes a linear function. Suppose I prepared one neural network model with the features of that trains on different images of cats and dogs. Now this dog is there. Here it takes the features of this image, and network is trying to learn and finally trying to predict whether this image belongs to a dog category or a cat category. Means it is predicting whether it is a dog and cat. So sometimes for some images we can easily features you can draw one line like a straight line. Without, here I am not using any activation function, I am directly using weighted sum and I am trying to predict the things. When I draw a line, for some images it is clearly we can draw one line between this dog and cat, means one category is cat, one category is dog, so prediction is easy. But it's but if we try to learn from other image, suppose I take this image, now network is trying to learn from this image. Some features may be mixed features, maybe suppose some features of dogs and cats are like they almost look like similar, like fur, and both of them has a 4 legs. Fur is also similar, both of them have a tail. So in these mixed features, while learning, it is difficult to draw a line between these features in neural networks. Then prediction is also, we can't predict whether this image belongs to a dog category or a cat category. Suppose if you say, when I draw a line, clearly I can't tell some mixed features, this line can't predict whether it's a dog or cat in this picture. Means these are all nothing but a linear regression wise problem. Why this problem arises? Because my weighted sum, I have taken weighted sum directly, so that is why it is acting like a linear regression. So the problem is, if we introduce a activation function in this neural network, means we are introducing a non-linearity, means it is a linear. If we without activation function it's a linear, I am introducing a non-linearity. When I introduce a non-linearity, means output of my weighted sum is sent as one input to one activation function that smoothens the values, like it is your values are between 0 to 1 based on the type of activation function we choose. It gives some output values. Here if I choose the sigmoid function, so it giving 0 to 1, then you can clearly see here this is sigma function. With this sigma function curve, now you can see you can expect one curve. Earlier if we don't introduce, almost every time it acts like a linear regression. Now when you try to draw this kind of a curve, we can easily categorize whether it's a dog or cat. Like this, activation function introduces non-linearity into the neural network, and it helps which neuron has highest value for activation. The decision is entirely taken care by our activation function. That is why they are very important in neural network. And we have different types of activation functions in neural network: sigmoid function, tanh function, ReLU, leaky ReLU, max out, and ELU. Each of these function has its own benefits, merits and demerits. Suppose I take a sigmoid function. Sigmoid function, it calculates its curve. You can see sigma a symbol 1 by 1 plus e power minus its function value, gives a values between 0 and 1. See, its output is 0 to and 1, a smooth way. So suppose a handwritten digit is there. Now my network is learning whether what is the digit inside this image. Is it a 4 or 2 or 7? It is also looking like a 7. So each feature of this is taken by this input layer. My entire hidden layer process this one. Weighted is finally it assigns this sigmoid function, assigns different values to the image. The image that has highest value here we got is a 4. That means it is smoothing the decision process. That is the advantage of introducing activation functions. It is smoothing entire decision process. When 0.82 means it's a 4, that 4 really matches with the image. So this one application of a sigmoid function. What are the different functions that are available, right? Sigmoid function, its output range is 0 to 1, it is smooth. Basically we use sigmoid function at output layer because most of the binary classifications either here there are only 2 classification, dog and cat. In such classification, if you apply a sigma function at output layer, it is easy for us to classify. Similarly, we can take a tan h function, formula for tan h function e power x minus e power minus x by e power x plus e power. So, output range is between -1 to and 1. Most of the output values are 0 centers. We apply these tan h functions inside hidden layers, like old models they are using tan h as in hidden layers, and most popular one is rectified linear unit ReLU. It takes the value of a 0 and a maximum, whatever the maximum value that it gives. So ReLU is also most commonly, ReLU is used in CNNs and deep neural networks and convolution neural networks. Most of the applications they take the ReLU. Old applications they take the tan h. When binary classification they go for the sigmoid, and sometimes mixed output layer they use a sigmoid, in a hidden layers they use a tan h, and type of the one. So ReLU has some problems, damaged nerve, some damaged neurons, dead neurons, it may not give a proper value. Then we have another one, leaky nerve, fixes dying ReLU problem, robust to dying neurons, softmax and swish. These are different type of activation functions we use while giving output to a neuron, means while deciding whether a neuron should be activated or not. In this there is one problem. Whenever you select a activation function, we should avoid this vanishing gradient problem. Vanishing gradient problem means your network is learning the value of a features of the data set. So if sometimes, because your sigmoid always gives 0 to 1, most of the outputs, if they are nearby 0, means there is no more learning. So neural network power is that it has to learn more features from the data set. If the most of the time outputs are near the 0, our gradient means back adjusting these weights is difficult. So slowly gradient moves towards 0, leading to vanishing gradient problem. That is possible in the sigmoid, that can be avoided by ReLUs. So these are different ways, types of activation functions available, and they introduce nonlinearity into the network, and they help us which neuron should be activated or not, that decision. So like this, activation functions allow us to capture more complex patterns, interaction and dependencies in the data rather than a simple linear model. So in next session we continue with our gradient descent and back propagation, another process in learning of a neural network. Thank you.